The Drexel Wireless Systems Laboratory, or DWSL, is an experimental wireless communication lab focused on prototyping of new technologies for a wide variety of applications. DWSL is located in 3101 Market Street in Philadelphia, Pennsylvania, and is a part of the College of Engineering of Drexel University. Projects in the lab span diverse topics ranging from new antenna technologies for 5G communications, to cybersecurity, to medical functional fabrics for the Internet of Things. Part of the Drexel Wireless Systems Lab is the GRID Software-Defined Radio Testbed, a network of several dozen software-defined radios. Unlike conventional radios that you might find in your local area networking products or cell phones, whose functionality is hard-coded into fixed hardware, a software-defined radio uses general-purpose hardware that can be reprogrammed in software to act like different devices and implement techniques that are not bound to the limitations of existing standards. Given the difficulties associated with field testing of wireless communication systems in diverse environments, it would be beneficial to have a testbed that can expose real radio hardware to realistic indoor and outdoor wireless channels in a controllable and repeatable manner. To address these challenges, we are building the Drexel GRID SDR testbed. This testbed is a unified experimental framework to rapidly prototype and evaluate a diverse range of wireless systems using 1. Field measurements to evaluate real-time transceiver and channel-specific effects, and 2. Network emulation to evaluate systems at a large scale with controllable and repeatable propagation channels. Hardware of the Drexel GRID SDR testbed consists of 1. The Echo Ridge DICE 24-port network channel emulator for multi-link emulation as well as hybrid measurement and simulation. 2. A centralized server for experiment management hosting Linux containers for each of the nodes in the grid. 3. Several dozen software-defined radios deployed in a ceiling-based network for over-the-air testing using omnidirectional or reconfigurable directional antennas. And 4. A wired network for routing RF, timing, and control signals to nodes for automated experimentation with the testbed. SDR platforms in the industrial and academic research community are focused on relatively small variations of existing standards. The Drexel GRID SDR testbed builds upon our work in developing a real-time, cross-layer, full radio stack software implementation, along with our experience in developing new antenna technologies for wireless communication systems. This flexibility and potential for cross-layer integration will be essential to consider a diverse set of applications, including cybersecurity, cyber-physical systems, smart cities, and the Internet of Things, without the constraints imposed by commercial standards. Existing wireless testbeds do not have real-time customizable and repeatable physical air propagation channels. We are using the Echo Ridge DICE channel emulator to create customizable and repeatable channels using industry-standard and custom channel models, while also enabling over-the-air testing in an indoor office environment with new antenna technologies that provide broadband and directional radiation pattern capabilities. Furthermore, we have developed a software layer to allow site-specific electromagnetic ray tracing to provide the far-field channels encountered by the radio and have demonstrated how this can be used for site-specific emulation for applications like drone, air-to-air, and air-to-ground communication channels. Some of the applications of the testbed include development of new antenna technologies. The lab is prototyping new electrically reconfigurable antennas that can change their radiation characteristics in response to the needs of the overlying communication network. We can test the radiation characteristics of these antennas in our anechoic chamber and our reverberation chamber, and then integrate these antennas with real radios running in the grid. Electronic warfare. The lab is prototyping real-time jamming systems that are capable of disrupting commercial communications. Since these jammers cannot be operated over the air, the use of large-scale channel emulation provides a unique opportunity to field test systems in realistic scenarios without fear of disrupting real systems. Medical Internet of Things. The lab is prototyping on-body sensor networks using flexible radio frequency identification tags integrated with fabric antennas. The use of channel emulation allows for these systems to be tested in a reproducible and realistic medical scenario prior to testing in real medical facilities. Drone-based communications. We are developing new technologies for drone-based air-to-air and air-to-ground communications in the presence of jamming. We have developed a technique to integrate results from electromagnetic ray tracing into our channel emulator so we can expose real radios to simulated environments. This capability allows us to experiment with drone-based communications in urban environments where real testing would be costly or challenging. Drone Collaboration Challenge. Drexel University sent Team Dragon Radio to the DARPA Spectrum Collaboration Challenge, or DARPA SC2. The competition required the prototyping of radios to sense and adapt to their surroundings, and radios that could collaborate with one another to make use of limited spectrum. Our entry into this competition, Dragon Radio, written by Professor Jeffrey Mainland, was recently released for open source use both by external users and in the Drexel Grid SDR testbed. Millimeter wave communications. While the majority of radios in the Grid SDR testbed make use of sub-6 GHz radios, several radios are now being upgraded to include 28 GHz radios for prototyping millimeter wave communication networks that will be a central component of 5G communications. We will use this experimental capability to field test new antenna technologies and networking techniques for 5G communications. The testbed has been leveraged for numerous undergraduate and graduate courses pertaining to analog and digital communication, wireless network security, and collaborative intelligent radio network design. We have also increasingly used the testbed to engage undergraduate researchers in experiential education projects through the Drexel Vertically Integrated Projects, or VIP, program. This exposure to hardware implementation provides valuable experience that cannot be obtained through theory and simulation alone. We are making our testbed available to external users to allow them to run experiments such as 1. Deploying radio containers with the ability to adjust the wireless channel between nodes, and 2. Evaluation of new antenna technologies with our customizable full-stack software-defined radio network. If you are interested in discussing potential educational projects or research collaboration using the testbed in these or other areas, please feel free to contact us. Thank you.